Study of fluctuations in the groundwater level in Rajasthan, a spatio-temporal approach. Abstract groundwater is a major source of fresh water in many parts of the world. Some regions are excessively dependent on it, leading to groundwater consumption faster than it can be naturally replenished and causing water tables to decline unremittingly. Rajasthan is the largest state in the country and water resources supporting the human population are very less. Rajasthan has its water problems. Moreover, it is undergoing an industrial transformation. The objective of the study is to identify the groundwater critical zones, study the fluctuation of groundwater level and analyze the trend of groundwater level for each district using the Man-Kendall Test. In this study, inverse distance weightage was applied for estimating the attribute values of locations that are within the database using known data values. Then the interpolated data values were extracted for statistical analysis using Man-Kendalls Test. Despite its importance, groundwater is poorly understood and often undervalued. Despite its importance, groundwater is poorly understood and often underestimated. Results show that the groundwater level had been at the most critical in 2010, i.e. -119 mbgl in pre-monsoon and -112 mbgl in post-monsoon. From 1996 to 2016, Man-Kendall's trend test illustrated a declining trend in Alwar, Dausa, Jaipur, Jaisalmer, Jhunjhunun, Sawai Madhopur and Sikar districts of Rajasthan. Keywords: groundwater level, inverse distance weightage, interpolation, Man-Kendall trend analysis. Introduction. Groundwater accounts for about 20% of the world's fresh water. But still less than 1% of all the water on Earth, comprising all ocean water and permanent ice. Groundwater refers to the water found beneath the Earth's surface. This water originates mostly from rain, melted snow, and other water that seeps through soil, or the cracks in the rocks. Due to gravity, the water moves downward, below the Earth's surface, until it hits a layer of rock or it can't get through, where it remains there and builds up. This section of water below the surface is called an aquifer. Groundwater can eventually go back up to the surface in the form of springs and wetlands, Jhunjhunun, 2015. In various places, groundwater discharged naturally into natural springs or contributed to rivers and wetlands. During droughts, groundwater often plays a vital role in sustaining rivers and streams and becomes a valuable buffer. Groundwater is a finite resource, and aquifers can become depleted when extraction rates exceed replenishment, or recharge, rates. Like surface water, groundwater can become polluted or contaminated. National Center for Groundwater Research and Training. The objectives of this study are to find the groundwater critical zones in Rajasthan, identify the seasonal variation of groundwater level and the trend of groundwater level and fluctuation. Rajasthan is a state with low to extremely low rainfall, intense summers with very high temperatures, high diurnal variation of temperatures and low humidity and high evaporation. It is one such Indian state with complex agroclimatic zones and in urgent need of expanding groundwater resources. Moreover, increase in population and urbanization leads to groundwater depletion. Thus, groundwater study plays an important role in assessment, monitoring, planning, development, and integrated water resources management in Rajasthan. 1. 2. Materials and methods. A study area. The present study focuses on water resources of Rajasthan and its districts. Rajasthan is the largest state in the country with total geographical area of 342,239 square kilometers and comprises of 33 districts, Yadav et al., 2016. According to 2011 census, it has a total population of 68,548,437. The state accounts for more than 10% of India's geographical area, supports about 5% of the human population and 20% of the livestock, but only possesses 1.2% of the total surface water and 1.7% of the groundwater available in India. The Aravalli Hill Ranges, running from northeast to southwest, divide the state approximately into the western arid and eastern semi-arid regions. Rajasthan's economy has undergone considerable transformation in the recent past, with agriculture, including livestock, providing 1/4 of the state's GDP. Approximately 5.4 million households are engaged in farming, while 60% of the state's population depend on agriculture for their livelihood. Rajasthan is heavily dependent on groundwater for irrigation, and about 90% of the drinking water and 60% of the irrigation water is sourced from groundwater supplies. The pressure on groundwater is further growing due to population growth and an increased number of industries. About 80% of the state areas have witnessed groundwater depletion, and many towns and villages have experienced a shortage of drinking water, particularly in summer months. Chetry, 2015. Fig.1, Location Map of Rajasthan. B. Methodology. Data was obtained from India WRIS WebGIS, cgwb.gov.in web link, which is a joint project of the Central Water Commission, CWC, Ministry of Water Resources, Government of India and Indian Space Research Organisation, ISRO, Department of Space, Government of India, to create a spatial database in MS Excel for the years 1996 to 2015, CGWB. Secondly, data was imported in ArcGIS software, and inverse distance weightage, IDW, was applied for estimating the attribute values of locations that are within the range of available data using known data values. The area of Rajasthan was clipped from the interpolated data using Model Builder. These values were extracted to MS Excel for statistical analysis. The missing data were calculated using the preceding and succeeding data using the following formula. +-3, 1. Where A equals preceding year data value, B equals succeeding year data value. The Man-Kendall test is a non-parametric method for identifying trends in time series data. The Man-Kendall test checks the null hypothesis of no trend versus the alternative hypothesis of the existence of increasing or decreasing trend. Narayan, et al., 2014. In SlowStat, using trend analysis tool, Man-Kendalls Test was carried out for the interpolated data. Each data value is compared to all subsequent data values. The initial value of the MK statistic, tau, is assumed to be 0, i.e. no trend. If a data value at a later time is higher than a data value of an earlier time, is incremented by 1. On the other hand, if the data value at a later time is lower than a data value sampled earlier, is decremented by 1. The net result of all such increments and decrements yields the final value of. Let x1, x2, xn represent n data points, where xj represents the data point at time j. Then, the mk, is given by equals sign, dash, equals +1 dash 1 dash 1, 2. Where, sign, dash, equals 1 if, dash, 0, equals 0 if, dash, equals 0, equals -1 if, dash, 0. A high positive value of is an indicator of an increasing trend, and a low negative value indicates a decreasing trend. Sen slope estimator provides an estimate of the magnitude of the detected trend and is calculated as equals, dash, dash. For I equals 1, 2, n, 3. Where 11 and xj are data values at time j and k, jk, respectively. The median of ss and values of ti is the Sen slope estimator. Equals, +1, /2, if n is odd, 4. Equals 12, 2/+, +2, 2/, if n is even, 5. Positive value of indicates an increasing trend, and negative value indicates a decreasing trend in the time series. Narayan et al., 2014. Overall methodology adopted in the study is shown in Fig 2. Fig 2, Overall methodology adopted in the study. 3 Results and discussions. There is a dynamic balance of water levels in aquifers between groundwater recharge, storage, and discharge. If recharge exceeds discharge, the volume of water in storage will increase and water levels will rise. If discharge exceeds recharge, the volume of water in storage will decrease and water levels will fall. It is because recharge and discharge are not distributed uniformly in space and time, groundwater levels are continuously rising or falling to adjust to the resulting imbalances. Read, 2012. Figure 2 to Figure 6 illustrates variations groundwater levels for years 1996, 2000, 2005, 2010 and 2015 has been shown for pre-monsoon and post-monsoon seasons. A spatial variation of groundwater level in Rajasthan. It can be proposed from the Fig 3, in the year 1996, the groundwater level in post-monsoon was as low as 104.64 mbgl and as high as -1.01 mbgl. In the year 2000, the groundwater level in post-monsoon was as low as 110.71 mbgl and as high as -1.20 mbgl as shown in Fig 4. It can be proposed from Fig 5 that in 2005, the groundwater level in pre-monsoon was as low as 110.97 mbgl and as high as -3.34 mbgl. Fig 6 proposed that in the year 2010 the groundwater levels in post-monsoon was as low as 119.99 mbgl and as high as -1.05 mbgl. We also found the critical zones have increased in the pre-monsoon. But in post-monsoon the groundwater level increased by -7.44 mbgl and maximum groundwater level increased to -0.26 mbgl. In Fig 7, the variation of groundwater level in 2015 seems to be more in the pre-monsoon season and the depth is as low as -118.24 mbgl and in the post-monsoon season, it is 110.50 mbgl. It can be seen in the figure that the groundwater levels in post-monsoon was as low as -118.24 mbgl and as high as -0.21 mbgl. The statistical techniques of Man-Kendall, MK, test and send slope estimator were applied to understand the trend of groundwater level of the study area during the study period on a temporal scale and also to forecast the future groundwater scenario. Each of the sampled groundwater fluctuation of the neighboring areas. Thus, the trend value reflects the overall groundwater fluctuation, BISVAS et 2018. Table 1 and 2 shows the trends in groundwater levels at different districts during pre-monsoon and post-monsoon. It can be observed from the tables that pre-monsoon, min, groundwater level in Ajmer, Alwar, Banswara, Bardapur, Bikaner, Chittorgarh, Kuru, Dausa, Jhalpur, Gangangarh, Hanumangarh, Jaipur, Jaisalmer, Jalari, Jhunjhunun, Jodhpur, Karoli, Nagaur, Pali, Pratapgarh, Sawai Madhopur, Sikar, Saroi, Tonk, Udaipur recorded a decreasing trend. On the other hand, Baran, Barmer, Bhilwara Bundai, Dungarpur, Jalwar, Kota, Rajsamund Hezan. Increasing trend. In case of post-monsoon, min, groundwater levels, Alwar, Banswara, Bhilwara, Bikaner, Chittorgarh, Kuru, Dausa, Jhalpur, Gangangarh, Hanumangarh, Jaipur, Jaisalmer, Jalari, Jalwar, Jhunjhunun, Jodhpur, Nagaur, Pratapgarh, Rajsamund, Sawai Madhopur, Sikar, Saroi show a decreasing trend. However, Ajmer, Baran, Barmer, Bardapur, Bundai, Dungarpur, Karoli, Kota, Pali, Tonk and Udaipur recorded an increasing trend. The groundwater levels in pre-monsoon, max, show a decreasing trend in the following districts of Rajasthan, viz. Alwar, Barmer, Bundai, Dausa, Jaipur, Jaisalmer, Jhunjhunun, Nagaur, Pratapgarh, Rajsamund, Sawai Madhopur, and Sikar. However, Ajmer, Banswara, Baran, Bardapur, Bhilwara, Bikaner, Chittorgarh, Kuru, Jhalpur, Dungarpur, Gangangarh, Hanumangarh, Jalari, Jalwar, Jodhpur, Karali, Kota, Pali, Saroi, Tonk, and Udaipur recorded an increasing trend. On the other hand, post-monsoon, max, groundwater levels of Alwar, Banswara, Bardapur, Dausa, Jaipur, Jaisalmer, Jhunjhunun, Sawai Madhopur and Sikar show a decreasing trend, while Ajmer, Baran, Barmer, Bhilwara, Bikaner, Bundai, Chittorgarh, Kuru, Jhalpur, Dungarpur, Gangangarh, Hanumangarh, Jalari, Jalwar, Jodhpur, Karali, Kota, Nagaur, Pali, Pratapgarh, Rajsamund, Saroi, Tonk, and Udaipur show an increasing trend. Conclusions. Man-Kendall's trend test was used to study the trend of groundwater levels in various network of observation wells districts of Rajasthan obtained from the Central Groundwater Board for both pre-monsoon and post-monsoon seasons. The critical zones have been observed majorly in the wells of Bikaner district over the years, followed by Jaisalmer, Jodhpur, Barmer, Ganganagar, Hanumangarh, Jhunjhunun, Jaipur, and Jalari. It can be proposed from the maps that the groundwater level had been at the most critical in 2010, i.e. -119 mbgl in pre-monsoon and -112 mbgl in post-monsoon. From 2010 to 2015 there has an increasing trend in groundwater level by -1.75 mbgl in pre-monsoon and 1.69 mbgl in post-monsoon. However, the critical zones are increasing spatially over the districts of Rajasthan due to population growth. Results from Table 1 and 2, it can be concluded that the minimum groundwater levels in the following districts viz. Alwar, Banswara, Bikaner, Chittorgarh, Kuru, Dausa, Jhalpur, Gangangarh, Hanumangarh, Jaipur, Jaisalmer, Jalari, Jhunjhunun, Jodhpur, Nagaur, Pratapgarh, Sawai Madhopur, Sikar, Saroi show a decreasing trend in both pre-monsoon and post-seasons. In contrast, Alwar, Dausa, Jaipur, Jaisalmer, Jhunjhunun, Sawai Madhopur and Sikar districts show a decreasing trend in maximum groundwater levels in both the seasons. Thus, Alwar, Dausa, Jaipur, Jaisalmer, Jhunjhunun, Sawai Madhopur and Sikar recorded declining trend in both maximum and minimum groundwater level and may need water conservation measures over the years. Acknowledgement. The author is immensely grateful to Central Groundwater Board, Rajasthan for providing the groundwater level data.